Imagine removing frozen water without ever allowing it to melt. It may sound impossible, but this is exactly what happens during pharmaceutical freeze drying. Instead of becoming liquid, ice transforms directly into water vapor. This process is called sublimation, and it is the driving force behind primary drying. Inside every frozen pharmaceutical product, water exists as tiny ice crystals. During primary drying, molecules at the surface of these crystals gain enough energy to escape directly into the vapor phase. Because liquid water never forms, the product maintains its delicate porous structure. This direct transition from solid to vapor is what makes lyophilization unique. Under normal conditions, ice melts before it evaporates. But inside a freeze dryer, the chamber pressure is reduced below the triple point of water. At this low pressure, liquid water is no longer stable. As a result, ice bypasses the liquid phase and becomes vapor directly, allowing drying to occur while the product remains frozen.
Vacuum alone cannot drive sublimation. The product also needs energy. Heat is supplied gently through the freeze dryer shelves, conducted through the vial, and transferred into the frozen product. This energy allows water molecules at the ice surface to escape as vapor. Even though heat is continuously supplied, the product remains frozen because the temperature is carefully controlled throughout primary drying. As ice disappears, it leaves behind a porous, dry layer. The boundary between the frozen region and the dried cake is called the sublimation front, where sublimation is actively taking place. Water vapor travels through these tiny pores and exits the vial. Larger pores allow vapor to escape more easily, while smaller pores increase resistance and slow the drying process. Once vapor leaves the product, it travels through the chamber toward the condenser, the coldest part of the freeze dryer. Here, the vapor freezes again and deposits as ice. By continuously removing water vapor from the chamber, the condenser maintains the driving force needed for sublimation to continue. The speed of sublimation depends on several process parameters working together. Shelf temperature supplies energy. Chamber pressure maintains the low-pressure environment. Product temperature must remain below its critical limit, while fill depth and ice crystal size determine how easily vapor can move through the dried cake. Balancing these variables is essential for an efficient drying cycle. A common misconception is that vacuum alone removes water. In reality, vacuum creates the right conditions, but heat provides the energy needed for sublimation. Heat alone is not enough either. Under normal pressure, ice simply melts. Successful pharmaceutical lyophilization always requires controlled heat and deep vacuum working together. Sublimation is the scientific foundation of primary drying. By combining controlled heat, deep vacuum, and continuous vapor removal, frozen water is removed directly as vapor, while preserving the product's structure. Understanding this process is the first step toward understanding how pharmaceutical lyophilization achieves stable, high-quality products. In the next episode, we'll explore how heat transfer, mass transfer, and process parameters work together to control the entire primary drying process.